Hello, my name is David Pecker, and welcome to Basics of Spaceflight. Today we're going to start at the very beginning and ask the question, where does space begin? As we look up in the sky, is there a sharp line that demarcates where there is atmosphere and where there is space? Or is there a smooth transition?
Looking at pictures from space, like this picture from the International Space Station, we can see the thin atmosphere above our planet, above planet Earth. And as we look at the atmosphere, we see that it gradually fades from blue to black, with no sharp line demarcating where it goes from being atmosphere to where it becomes space. But now let's get to the bottom of this question. Let's start by drawing the ground, and here I draw a little blip. This is Mount Everest, which is the tallest mountain on Earth, with an altitude of almost 9 kilometers. Also, Mount Everest is approximately the height at which the air becomes too thin to breathe, and only the craziest mountain climbers can go all the way to the top of Mount Everest without supplemental oxygen. Now, you've probably flown on commercial airliners. Here is a picture of a Boeing 787. It's the latest and greatest airplane from Boeing. It's actually made mostly of carbon composites. It's a plastic airplane. And it can fly at an altitude of 13.1 kilometers. So just slightly higher than Mount Everest. Well, commercial airliners don't fly that high, except for this one. This is the Aerospatiale BAC Concorde. And it is a supersonic airplane that used to fly, and it flew at a crazy altitude of 18 kilometers, which is approximately the highest altitude for normal airplanes, including military aircraft, to fly at. It turns out that it's possible to make a balloon that flies much higher than an airplane. This is a picture of a NASA Big 60 balloon. This balloon, when it's fully inflated at altitude, becomes the size of not a football field, but a football stadium. It's absolutely a gigantic balloon, and it can fly to an altitude of almost 50 kilometers. Actually, the world record for a balloon flight was set by a Japanese team who managed to fly their balloon to 53 kilometers in height. So far, we have discussed only conventional airplanes that use jet engines, and jet engines basically push on the air around the airplane to propel the airplane forward. Here pictured is a rocket plane, and rocket plane works on a completely different principle. And we will discuss this later in the class, but the basic idea is that rocket airplane throws back reaction mass, and that propels the airplane forward. Now, a rocket plane can fly to much higher altitude, and in fact the X-15 pictured here flew to an altitude of 107.9 kilometers, which is really, really high. Oh, and by the way, the gentleman standing in front of the airplane is none other than Neil Armstrong, who was the first person to step on the moon. But how high can an airplane fly in sustained flight? The answer to this question comes from Theodor von Karman, who was a Hungarian mathematician, physicist, and aeronautical engineer. He is actually known for quite a few things. One of the things that he developed is the understanding that swept back wings are important for supersonic flight. But his contribution to high altitude flight is the following realization. As you fly higher, the airplane needs to fly faster to generate enough lift to stay up. And in sustained flight, in Earth's atmosphere, you have to fly at approximately orbital velocity once your altitude becomes about 100 kilometers. So this barrier at 100 kilometers is basically the edge of space. This is where an airplane becomes a spacecraft, since it's flying as fast as a satellite. Now, this 100-kilometer line is an arbitrary line, and different space agencies define the height at which space begins differently. So the 100-kilometer von Karman line is a definition used by Fédération Aéronautique Internationale, which is the International Aeronautics Federation. NASA defines it differently. It defines space at 50 miles in altitude, which means that a lot of X-15 pilots who did not fly all the way to 100 kilometers actually got their astronaut wings as they surpassed 50 miles, but not 100 kilometers in altitude. Now you might ask yourselves, how did X-15 manage to fly above the Karman line? And the reason is that it cheated a little bit. So here is a picture of the F-15 flight path, and you see that some of the flight paths go horizontal, while others go up and then down. And the up and down path are the ones where the X-15 attained maximum altitude, and it did this basically by burning its rocket engine to accelerate the airplane up, and then it coasted over the top, reaching maximum altitude, but not, of course, in sustained flight. Okay, so now that we have established where space begins, how high do actual spacecraft fly? Well, typically spacecraft tend to fly at an altitude of about 300 kilometers, and the reason for this is that there is still residual atmosphere up there, which tends to slow down the spacecraft and decays orbit. However, there are parking orbits which are much lower in altitude. For example, pictured here is a Apollo spacecraft, and on its way to the moon, it made a little pause in a parking orbit at an altitude of about 160 kilometers. This pause was used to figure out that the spacecraft was healthy before the translunar injection burn sent the spacecraft to the moon. Now, typically people say that space is really far away, but that's not true. As we saw, it's only about 100 kilometers straight up, and that's about the same as the distance from University of Pittsburgh to Cadiz, Ohio, or half the distance to State College, Pennsylvania. Well, if space is so close, why is rocket science so hard? As we see in the picture, Google tells us it only takes an hour to drive 100 kilometers. Well, the reason is to get to space, we not only need to get to 100 kilometers in altitude, we also need to reach orbital velocity, which is really quite fast. It's 28,000 kilometers per hour. And that is actually the hard part. To conclude, let us watch a video of a space launch and see what we can see. Specifically, we will take a look at the SpaceX launch of a Falcon 9 rocket. As you watch the video, I would like you to keep track of a couple things. First is how long does it take the rocket to reach space, that is 100 kilometers of altitude. Second, how long does it take the rocket to reach orbital velocity, that is a velocity of 28,000 kilometers per hour. And finally, I would like you to watch in which direction the rocket is flying. When is the rocket flying straight up, and when is the rocket flying sideways? Specifically, as you look at the rocket, look at how it's gaining altitude. Does it keep gaining altitude once it gets to space? Or does the altitude gain slow down and the rocket is flying mostly sideways and accelerating? And why do you think the rocket is flying in the way it is?
Vehicles configured for flight.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ignition. Liftoff of Falcon 9.
Vehicles pitching downrange.
Stage 1 props nominal.
T plus 40 seconds and Falcon 9 is on its way with a countdown of the last 10 seconds by Iridium CEO Matt Desch. We're throttling down now in preparation for the period of maximum dynamic pressure.
Vehicle supersonic.
Garcia on countdown 1, first motion time 15:31:33.492 UTC.
Calling out the time there of liftoff over the net.
Acquisition of signal.
We're through the period of maximum dynamic pressure.
Maximum aerodynamic pressure.
Merlin engines continuing to perform at 1.7 million pounds of thrust. Falcon 9 heading out into the upper atmosphere. Nice view from the first stage camera looking aft. We're headed south from Vandenberg Air Force Base, Space Launch Complex 4 East.
MVAC engine chill.
The MVAC engine cheer call out indicates that we have now opened up the oxygen that goes to the pump on the second stage engine. chilling it down for ignition coming up about a minute from now. We're hearing good callouts. Propulsion looks nominal. The trajectory looks good. Now coming up will be rapid fire events. Main engine cutoff. We shut down the 9 Merlin 1D engines. At 2.5 minutes, we will separate the stages. We'll light the second stage engine, and at just a little bit after that, we'll relight 3 engines on the first stage to begin slowing it down for a landing in the Pacific Ocean on our drone ship.
Stage separation confirmed. And back ignition.
Stage 1 has entered its flip.
So we've had successful shutdown of the first stage. It's separated. It's doing the flip to reorient, and it's lit its 3 engines to begin slowing it down to come to the drone ship. Meanwhile, on the right-hand side of the display, second stage engine has ignited, begin propelling the Iridium satellites. You can see them there as we get ready for fairing separation.
Fairing separation confirmed.
Stage 1 boost back shutdown.
A lot of events happening. You saw the fairing separate, and you can see one half of the fairing drifting away behind the second stage on the right-hand side of the display. On the left side, we've had shutdown from the boost back burn, and you can see the titanium grid fins slowly extending. That's nominal for those grid fins. The white flashing you see, that is attitude control gas, nitrogen, that's used to orient the first stage. We're coming up 4 minutes into flight. In about a minute and a half, the first stage will initiate a quick re-entry burn to again slow the rocket down as it re-enters Earth's atmosphere. A minute later, we'll perform the final burn, the landing burn, which will decelerate the vehicle to a gentle landing atop our drone ship. Just read the instructions. Now, as a reminder, recovery is always a secondary objective to our primary goal of delivering our customers' satellites to orbit. Views you have right now, the camera on the left is looking up the inner stage where there used to be a second stage. Now we're looking at the grid fins with the Pacific Ocean in the background. Meanwhile, on the right-hand side, the MVAC-D second stage engine running about 200,000 pounds of thrust in the vacuum of space. You can see the nozzle glowing red hot. That's nominal for that nozzle. We're about half a minute away from the entry burn. This one will also be a 3-engine burn. That'll slow the vehicle down as we go to subsonic speeds, and then eventually a final burn a little bit after that to land on the drone ship. Getting excellent views as the sun has risen recently over the west coast here in the United States.
Stage 1 entry burn has started.
Call out the entry burn on stage 1 has started. 3 engines up and running.
Stage 1 entry burn shut down.
And the entry burn shutdown called out over the countdown net, as you heard.
Stage 1 FTS is saved.
Everything continuing to look good. First stage entry burn has ended. We're less than a minute until the third and final landing burn, followed by touchdown on the drone ship. And you can see the first stage descending back down through the atmosphere as it's coming up on the cloud deck. Now, as a reminder, we may lose live video
Stage
coverage
1 is transonic.
on the drone ship as the engine exhaust degrades the radio frequency signal. Now, if that happens, we'll share status updates on the first stage as they become available.
Drone ship, AOS.
Drone ship AOS means the drone ship has acquired
Stage
the
1
signal.
landing burn has started.
Center engine has lit. We're slowing ourselves down, preparing to find the drone ship right underneath us. You've got the camera view from the drone ship now. Waiting to see the first stage come into view. And we're getting the signal dropout, which is not unusual. We're gonna keep pressing on. We have not heard confirmation.
Falcon 9 has landed. Landing operators moving to 11.1 high.
There you go. We heard the call out from recovery. Falcon 9 has landed. We hope to get a shot of it on the deck of the drone ship a little bit later, but we can confirm we're down with the first stage. We're pressing on the second stage mission. Currently, trajectory looks good. We've begun throttling down the Merlin vacuum engine, maintaining the G load on the Iridium Next satellites. And we've got the view back from this drone ship. There it is, right in the middle of the bullseye. The first stage is back again down on Earth. Meanwhile, second stage is getting ready in less than 20 seconds for shutdown and entry into the parking orbit.
Stage 2 FTS is safe.
Coming up on shutdown of the second stage engine,